Forces, Newton's first law, the law of inertia. Motion, Aristotle to Galileo. Aristotle, a Greek philosopher and scientist, lived from 384 BC to 322 BC, and he uses common sense to explain physics. He noticed that some object in motion maintained their motion without assistance. He called these natural motions. These included rocks falling off ledges, liquids running downhill, air rising, and flames going upward. These were two of the fathers, I guess you could say, of physics. So Galileo built off of Aristotle and yada, yada, yada. Okay, so his view was that any solid falls toward the earth because it seeks to get closer to its natural resting place. Any motion that was not natural was violent motion. That is, the object needed to be pushed or pulled. Aristotelian physics had a hard time explaining many things, though sadly most people still share his views on motion. Consider this. What happens when you drop two pieces of paper? One is flat and one is crumbled into a ball. So you take two identical pieces of paper, you crumble one up, and the other one you don't do anything, and you drop both of them. What's going to happen? So here's our picture down below. Let me turn my pen on. Here's our picture down here of our crumpled up paper and our not crumpled up paper. Okay. The masses are the same, but they fall at different rates. So in the last unit, we had things freely falling, right? We assumed that there was no air resistance, and we noticed that everything fell to the earth at the same rate because they were all experiencing gravity, right? But here we notice that if you crumple up a piece of paper, it falls faster than a piece of paper that hasn't been crumpled up, and you should try this on your own. The masses are the same, but they fall at different rates. Why is this? What happens when you drop two objects of roughly the same shape but very different masses? What happens when you drop two objects of roughly... Okay, so even with different masses, they both hit the ground at the same time. So this is typically happens as long as air resistance isn't affecting them differently. Aristotelian physics could not explain either of these effects. His theory stated that the heavier object would seek the Earth's center more strongly, thus falling faster. And although Aristotle was a brilliant person, and we owe a lot to him, this is an incorrect. We now know that this is not correct. That was his theory, and it's been proven incorrect. We can test the hypothesis that any two objects dropped from the same height will hit the ground at precisely the same time using a vacuum, a container that contains no air. This has been tested and the objects fall precisely at the same rate. This leads to an important discovery by Galileo, Galileo's law of falling. And Galileo lived a little bit later, 1564 to 1642. Galileo stated that if air resistance is negligible, that means it's not, there's not enough air resistance to cause any, it's not that important, then any two objects that are dropped together will fall together, regardless of their masses, shapes, or materials. This means that any two objects, a duck, a velociraptor, a notebook, a piece of chalk, even an individual atom will fall together. All objects fall at the same rate in a vacuum. So Newton's first law, so Galileo's law of falling is, astronauts confirmed this on the moon as well. A hammer and a feather were dropped together from the same height on the moon and fell at the same rate, hitting the moon's surface at the same time. I also have a video of a feather and a bowling ball being dropped at the same time in a vacuum. A cool fact, the falling of an individual atom was tested in 1999, and in order to do so, the researchers had to eliminate any thermal motion the atom had. This meant cooling the atoms within 2 millionths of a degree of absolute zero. The atoms fell just like stones. Galileo made many other contributions to the study of forces, including the recognition of the effects of friction and being one of the first scientists to use the scientific method. His contributions helped future physicists develop the 3 laws of Newtonian physics. You've heard inertia is a property of matter, from the opening credits to Bill Nye the Science Guy. But what exactly is inertia? So we hear inertia a lot, but what is it? Inertia is an object's tendency to keep moving or remain at rest, to maintain its motion. This leads us to Newton's first law, the law. Newton's first law is oftentimes referred to as the law of inertia. So like, think about this. If you hit a hockey puck, and assuming that there's no friction on the ice, the object's tendency is going to be to keep moving, okay? Or if you have a cup on a table, that cup is going to keep sitting there at the table, not moving, because it wants to stay in the state that it's in. So an object's tendency is to keep moving or remain at rest to maintain its motion. So it wants to stay in whatever state it is. And you can also think about this in terms of like a skateboarder. If a skateboarder's riding a skateboard and his skateboard hits a rock, what happens to his body? His body keeps moving forward because it was moving forward, and when the skateboard stopped, his body wanted to keep moving forward because of inertia. This is important. It's first law of motion. You need to make sure you know, make special note of this. It's often referred to as the law of inertia. And here's a more specific definition of Newton's first law of motion. An object that is subject to no external forces will maintain its motion. It will remain stationary or keep moving with the same constant velocity. You may have also heard it stated as an object at rest remains at rest, and an object in motion remains in motion unless acted upon by an external force or non-zero net force. Consider an object in space, far from the gravitational forces of other objects in space. If the object was stationary to begin with, then it will remain stationary until an external force acts upon it. Similarly, if the object was moving, let's say if you're up in space and you're in a spacesuit and you throw a ball in space, that ball is just going to keep going constantly. It's just going to keep moving in that same direction at that same speed because there's no air resistance or anything, no gravity, nothing that's going to cause, no external forces on that ball. It will continue at that constant velocity until an external force acts upon it. Draw these situations to help remember Newton's first law, the law of inertia. So here's a stationary object, and notice that the velocity is stationary. You can know it's stationary because it's got v hat with equals 0 meters per second. Okay, and here is an object with constant velocity. So see, this is constant. Okay. So Newton's first law. So obviously after Galileo, Newton eventually came and he came up with the law of inertia, or Newton's first law. It says, use Newton's first law to explain why it is important to wear your seatbelt in a moving vehicle. So pause the video and try to explain that. Okay, it is important to wear your seatbelt because in a collision, the car stops, but you keep moving unless there's a force to stop you. This is similar to the skateboard situation where the skateboarder, if the skateboard hits a rock, the skateboarder will end up flying forward. And this happens in a car. So if you, trying to select this. If you're in a car and you're driving along and you're sitting in here, and then if you have a collision and you don't have your seatbelt on, you and your car were moving forward, but when your car stops, you continue to move forward. And so without a force to stop you, the seatbelt, you keep moving. Any questions?